Hello, in this video I'm going to talk about the longest common subsequence algorithm, also known as the LCS. It is a dynamic programming based algorithm for finding the longest common subsequence in two strings. So say I have a string, I have two strings x and y, and their problem space contains 1 to m elements and 1 to n elements. And our job here is to find the longest common subsequence between these two strings, x and y. To do that, a naive approach would be to iterate through either of the strings and start checking. Once we find the match, then keep on checking till we find a problem, till we find a substring that matches in both the strings. But the time complexity for this would be pretty high because, for one, we need to use combination here. So there could be 2 to the power of m possible combinations of substrings here. Similarly, 2 to the power of n possible combinations of substrings. Add those two, it becomes an asymptotic time complexity of 2 to the power of m plus 2 to the power of n, which is, and I'm misusing notation here again, 2 to the power of, say, big M, which is an exponential time complexity, and we do not want that way in polynomial. So to do this, we need to figure out the cases that would be there. So what's the base case here? So if I have a matrix, a two-dimensional matrix of, say, m and n elements, I have, say, m elements here, n elements there, would be the other way around, doesn't really matter, but for the purpose of this example I'm going to take it that way. And I have, say, that many rows and columns. So if I say I'm going to match a zero based, say I'm going to match x of 0 and j, and here I take I to iterate, and here I take j to iterate, and I say I'm going to match x of 0 and j. So x is always 0, so of course I will find 0 matches. Similarly, if I say I'm going to match I of 0, where y is always 0, I'm going to find 0 matches. So those two are our base cases. Now, going away from the base case, what other cases can we have? Now, there could be two obvious possibilities. One, if there is a match, and the second, if there is no match. So like any other DP based, dynamic programming based problem, we try to reduce the problem space. We take a big problem space, we break it down, chop it into pieces, and call it a subproblem, and then we repeatedly solve subproblems, and we use the results from previous subproblems to solve the other subproblems. And that's how we solve pretty much all dynamic problems. So what's a recursion equation here? Not considering a dynamic problem, if we had to solve this by recursion, what would be a recursion? What would be a recursive equation for this problem? So we say we need to find LCS of x and y, and we want to figure out recursive equation for this one. So like we discussed, there could be two broad possibilities: if xi equals to yj, and if xi is not equal to yj. These are the two broad possibilities. Now we said that we want to reduce our problem space. So if we are reducing a problem space, we are actually trying to do a bottom-up approach. So if we do find a match, we say, okay, we found a match, well done, pat on the back, and then we go to a smaller problem space and we try and figure out whether we can continue finding matches there. So I shouldn't have put x and y here. Let's say ij, because I really want to use those two notations. Again, playing with notations, you could use anything you want. So we say LC is I minus 1, j minus 1 plus 1, because we found one match. That is if we find a match. So we go back a step in both the arrays, or in both the strings, and we say do the same thing for the rest of it. But what if we don't find a match? Then there could be two possibilities here. And we want to take, since we are computing the longest common subsequence, we want to take the longest possibility, or the largest possibility, which mathematically means a max. But max of what? So it could be that if I go a step back in y, I might find the longest possibility. Or if I go a step back in x, I can find the longest possibility. I don't know that, so I have to compute both and then find the max of both. So I say LCS I j minus 1, or LCS I minus 1 j. The max of that will obviously give me the longest palindrome. I'm sorry, longest common subsequence. Now that's the recursive equation. And why do we need dynamic programming here? I mean, we got recursive equation, might as well just call it in and we're done. But why does everybody go for dynamic programming here? So say for instance, I want to find the LCS of, I don't know, 2, 3, small one, sounds about right. So if I do the recursion tree for this one using the recursive equation that we just figured out, if there is a match, we will go 1, 2. I'm not writing, I'm misusing notations here, and I'm not writing LCS, but it should be LCS 1, 2. I guess I'm just too lazy. Or it could be max of 2, 2, or max of 2, 2 and 1, 3. Beyond that, it could be 1, 1. This one could go in for 1, 2, or 2, 1, and this could go in for, if we are taking a zero based index, 0, 3, or 1, 2, right? And this could of course go for 0, 0. I'm sorry, it actually will have more steps. I still need to put in I, j minus 1 and all these things. So this could be 1, 1, or it could be 0, 2, and so on. Notice that we have repeated subproblems here. We have 1, 1, we probably have 1, 2, and there is more to come if we continue with this equation tree. So that is why we need a dynamic programming approach to this, because although we have a very good recursive equation and that could possibly solve the problem, that will definitely solve the problem, but we don't want to increase our recursion stack here. So since we have overlapping subproblems, as we can see from this recursion tree, we would prefer if we could use dynamic programming here. So how do we do that? Notice that if when we are computing 1, 2, it depends on 1, 1. Again, when we are computing when you're computing 2, 2, it depends on 1, 2. Again, when you're computing 1, 3, it also depends on 1, 2. So no matter who gets there first, somebody will get there first and compute 1, 2. So the next computation, which depends on 1, 2, need not compute 1, 2 again. What is 1, 2? That's the longest common subsequence, the length of the longest common subsequence till that point. So all we need is a two-dimensional array or a matrix, and we have a matrix. That's 1 and 0, 1, 2, 3. So that's 1, 2 for you. So whoever gets there first fills that up. And the next call, the next recursion call, when it comes through, it just says, hey, there is a, that has been filled up and I can find the value from there. So I just will not get into another recursion stack and just send back the value from there. Now, it might seem a little trivial because there is nothing after 1, 2 in this diagram, but there will be, because I haven't made the entire recursion tree. And when there is a huge recursion tree, and if you can avoid, say, 4 levels of stack memory, that's quite an expensive operation to avoid. So that is why you require dynamic programming. The code is very simple. You just use this recursion equation along with memoization, where you use a two-dimensional matrix and store in computed values and recall those values when you need it at a later stage. So that's your longest common subsequence problem. Hope you find this useful. Thank you.